First things first, what's a prime number?
A number that is only divisible by itself with 1.
A number that is divisible by only itself and 1, and also
1 is not prime.
And also 1 is not prime.
That seems exclusionary.
It does seem exclusionary. You could make an alternate definition of the word prime, but then there would be a problem with this thing we really like to use a lot called the unique prime factorization theorem, which essentially says that you can take a number like 6 and you can write it as a product of primes to powers. This one specifically is 3 to the first times 2 to the first, and that expression is unique. If I allow 1 to be prime, then I'd have to deal with, like, well,
1 to any possible power.
yeah. 3 times 2 times 1 to the 17th is 6. But it's also 3 times 2 times 1 to the 347th. Right? Like, and then I'd have to make this caveat in my prime factorization theorem, and that would be kind of silly. But certainly it would not surprise any mathematicians if the aliens banging on the door banged 1 as a prime. Like, we would all be like, not the finest choice, but I guess you have space travel. Okay. Right? So, you know, we'd kind of negotiate on that one. What I want to develop is, 1, a motivation for why you care about prime numbers, and 2, a method by which to find them. You guys know why you care about prime numbers?
They're useful in mechanical engineering stuff.
Yeah, I'd say you guys care even more because you're in an intro programming class. Like, yeah, they're good for math and thus kind of good for engineering, but there's one thing that computers do a lot of that this is really crucial for. Do you know what RSA is? Okay, when you use your credit card to pay Amazon, how do you know that the guy at your internet service provider isn't just watching that number go across the screen and going, sweet, I'm gonna spend this dude's money too? Right?
Encryption.
Yeah, this is some kind of encryption algorithm. It's probably RSA encryption, give or take a little bit. There's a bunch of different flavors of RSA encryption. But basically, RSA encryption relies on having 2 really big prime numbers that are kind of kept a little secret, right? And the fact that it's hard to guess prime numbers kind of makes this a viable encryption algorithm. If you came up with an absolutely perfect way to tell instantaneously whether a number was prime or not, like without having to do a little calculation, you would probably break RSA encryption in a hurry. If you knew a way to factor a number into its prime factors immediately, like magic, tap, boom, factors, you'd really break RSA encryption. Basically, it just relies on the fact that it takes a really long time to do that factoring, and transactions are pretty fast. It's cool, that? So that's why you care, because encryption algorithms. Now, how you go find some prime numbers is a thing that goes back to the Greeks. So, I need to say a name, and I had to write it down because I've been pronouncing things wrong lately because I'm an idiot. Yes, I was pronouncing demois wrong. So I want to show you guys the sieve of, and I'm going to write this before I say it. Eratosthenes.
Oh, isn't this the guy who, like, mathematically proved the Earth was round?
I don't know,
Well,
actually.
yeah, he found the distance from Alexandria to this other city and observed the angle of the sun at noon at both locations, and from that he figured out the
The radius.
of the Earth.
Yeah.
So maybe not necessarily demonstrated that the Earth was round,
I
but
just remember,
calculated
like, oh,
the
he's
radius.
the guy who, like, figured out the Earth's like, circumference or whatever.
Yeah.
Yeah, and of
Same
course, if
guy.
you know the radius, right, you know the
Yeah.
circumference
Yeah.
pretty immediately. So I'm gonna make a pronunciation key that's not phonetically good, but Eratosthenes. Okay, what's a sieve?
It's like
It's just a shaky filter thing, right?
Shaky filter thing. Yeah, exactly. So the way the sieve of Eratosthenes works is you write down all the numbers.
all of them.
Yeah, for real.
That's gonna take a while. So see if you take
Okay. And then what you do is and because we're going to code this, and because this is computer science class, so just start counting at 0. And then you kind of take yourself some thoughts. So first things first, 0 is not prime. Cross that off the list. 1's not prime. Cross that off the list. For the rest, you say, okay, 2 is prime. And then you go through and cross off all the multiples of 2. So 2's prime. Sorry, I need my green marker. Check. 4 is not, 6 isn't, 8 isn't, 10 isn't, 12 isn't, 14 isn't. Why not?
Because it was 2.
Because they're all multiples of 2. So then you go to the next number. 3's not crossed off, so that one's prime. And then you go through and cross off all the multiples of 3. So I'm crossing off 6 again, and 9, and 12 again. And then the next one will be 15, right? And you could notice, right, that the next one after 15 is already crossed off. You guys see that?
Yeah.
Why are those ones already crossed off?
Because they're divisible by 2.
Yeah, because those were ones that were divisible by 2, right? Okay, so then you'd go to your next number. What's your next number? 5? 5's prime.
I mean,
You might loop through 4 and say, 4, I already crossed 4 off. Pitch it, right? Next, 5. 5's prime. Why is 5 prime? Like, why do I know 5 is prime?
Because it wasn't crossed out.
Yeah, because it wasn't crossed off. That's the cool thing about the sieve, right? If you get to a number and it's not crossed off yet, it's prime. With the exception of 0 and 1 by definition.
right.
It's cool with this? So, 5's prime. Then I need to go through and cross off the multiples of 5. 10, 15, 20, 25 is kind of the first new one, right? The first one that's not already crossed off. And then I come back to the front of my list, right? And I go, okay, so 6 isn't prime because I crossed it off earlier. So 7 is. And then I'd go cross off multiples of 7.
14.
You guys cool with that? And really you'll have to go out to that thing squared before you start finding anything interesting. You guys see why? Because all the earlier multiples, right? Like, I already crossed off 7 times 3 because I crossed off all the multiples of 3 earlier. So you really can do some efficiency with this algorithm. When I code this, I'm not going to code an efficient algorithm for this. I'm just going to code the dumb one, and we're just going to cross off lots of things that are already crossed off. if you wanted to spend some time and like fiddle with the efficiency, you definitely could do better than the thing I'm gonna make. Let's see. So then what would I do? After I found 7's prime,
11's
I'd walk out 8's not, 9's not, 10's not, 11 must be. Then I'd go cross off multiples of 11, and then I'd go find 13. You guys see this? So far, on the board here, I managed to find the primes up to...
13.
Yeah, I think actually I've got all the primes up to 15, right? And actually a few, like, a couple more, right?
And by extension, all the primes up to 13 squared.
Yeah, that's not necessarily obvious, but is true. That's that thing I was just saying about, well, the first kind of new interesting thing happens when you get to 13 squared, or when you get to whatever squared, right? Because you already dealt with all the earlier multiples. So yeah, if I had written this list out to 169, by crossing off the numbers up to 13, I'm done with up to 169. And I could just go through and circle all the ones. You guys see that? So really, if you want to check all the numbers up to 100, how far out in this do you have to go?
10 7.
Yeah, you just have to go to the square root of 110. That's cool, huh? Okay. So, sometimes this thing's called a prime number sieve. It used to be that this thing was, like, actually a shaky little deal. People used to actually make cardboard cutouts with all the multiples so that they could cross numbers on. This was, no joke, a source of, like, much human labor to calculate big prime numbers.
Why do they want big prime numbers?
No idea.
Because math.
Yeah,
Well, I guess back then you just had old dudes who wanted to do math and lots of money, and there's young dudes who kind of wanted to do math and no money. So you would just pay the young dudes to do the dumb math, the old dudes to do the big math. Right?
so there are a number of interesting questions that you can ask about prime numbers that, like, looking through the sieve would kind of help you answer. But in my knowledge of where the RSA encryption algorithm first came from is pretty sparse. I don't know the dating on that object. I don't know if it dates to far enough back to have been a reason for finding primes in the Middle Ages. The things like the twin prime conjecture. So what's a twin prime?
It's two primes that are similar.
Yeah, like two primes that are similar, born together, maybe?
Like 2 and 3?
Yeah, so that's the last one that's next to each other, right? 2 and 3? Why is that the last one that's next to each other?
It's the only one.
The only one that's next to each other because...
Every even number.
Yeah, because you went through across all the evens off, right? So what's the closest they can be, other than 2 and 3?
At least.
Yeah, they could be like this pair, or this pair, or this pair,
Right.
right? So these are twin primes, pairs of primes that are separated by just an even number that's been crossed off. That's cool, huh? And then there's conjectures like, are there infinitely many twin primes? The answer to that one's yeah.
Probably, yeah.
Are there consistent spacings between twin primes?
I mean, didn't you just define what the spacing was?
I mean between pairs. So like
Oh, okay.
these two are these two pairs are pretty close together. As you go out, that spacing gets a little bit bigger, but at what rate does that spacing get bigger is kind of an interesting question.
Can you write a function for it?
Yeah, could you write a function for it, or could you kind of do that, like, I didn't really talk about ordering for, so remember when we were talking about sorting algorithms and we were saying this sorting algorithm is kind of better than this one because it kind of resolves faster? We could ask about the order of growth at least, like how fast does this get bigger as you go further out? Those would be interesting questions. And these have interesting consequences to lots of kind of number theory stuff.